I think we have already discussed about the fact that this whatever we see in CMB, the anisotropies in the CMB, and the large scale structure that we see today are basically originated as quantum fluctuations. So in this talk, I basically briefly explain the quantum evolution of these primordial fluctuations. Yeah, actually these quantum fluctuations are everywhere. These vacuum fluctuations are everywhere. So they are simply oscillating, locally oscillating in a potential well, right? So around the minimum. So they are just simply, oscillating, relaxing comfortably. So in order to, make them useful to do something, someone has to pull out, pull them out from the potential well, right? So this is what inflation does. So this is something usually, Sriram used to tell to me that if you want to become something, you have to come out of the potential well, and you have to come out of the, comfortable place. So this is what inflation does here. So there are fluctuations, quantum fluctuations, and the inflation just pull the fluctuations out of the potential well. So during this inflation, the horizon of the universe expands exponentially. But the Hubble radius, which is actually the measure of space-time curvature, that remains almost constant. And the wavelengths associated with these quantum fluctuations also increases exponentially. So what happens is that these wavelengths become larger than the wavelengths associated with these fluctuations become larger than the Hubble radius. So it starts to see the curvature of the space-time. Okay. So this is the Hubble radius. So this is the wavelength associated with the fluctuation. Some of them are inside the Hubble patch, and some of them are outside during the evolution. And when this length scale associated with these fluctuations become comparable to the Hubble radius, which is a measure of, as I said, which is a measure of curvature of the space time, comparable with the length scale associated with then it starts to see the geometry of the space time, which basically means that these fluctuations start to interact with the pattern, and then okay. So basically, is that so during this evolution of fluctuation, inflation makes that associated with fluctuation, as I said, it's a potential well when simply oscillating, it becomes inverted. The potential becomes negative. So the oscillator becomes inverted oscillator. So in inverted oscillator, we know that the fluctuations simply grow or decay. So in reality, so we deal with not what we have is each point in the space infinite number of oscillators. So we cannot simply talk about the one oscillator and do the physics. So we have to take the average over a path, average of amplitude of fluctuations over a path, and do the physics. So here these are the small patches inside the radius, and then this dashed, this circle, white circle, size of the Hubble radius. So when this, as I said, when the length of these fluctuations become larger than the Hubble radius, we start to see the curvature of the space-time. So when this the patch size of the patch becomes larger than the Hubble radius, practically we can show that these patches become independent and evolve independently without interacting with other patches, like separate universe, separate homogeneous universe. Okay. So that is what happened during inflation. We have now separate universe evolving independently. But when the universe goes to the radiation dominated or matter dominated, the horizon becomes almost equal to the Hubble radius. So these patches become inside the horizon. So they start to form, you know, different structures. So this is the story of the quantum fluctuations. How the quantum fluctuations become the structures in the universe. Okay. So this is just a story. So the physical we ask is that how much quantumness. So I said these are originated quantum fluctuations. How much quantumness, they remember about the quantum origin. So we calculate this or we analyze this correlation function at the end of inflation or radiation domination or matter domination. So they are classical correlations. So the question is how much these patches or different structures know about their quantum origin. Okay, so there are different measures available to quantify the quantum mass. Some of them are excusing and excusing basically that if in phase space if you calculate the correlation functions, how much the dispersion in one of the direction is larger than the other. So that is what using and we can measure this using in terms of this parameter. That is one of the measures. And there is we can measure the quantum using quantum correlations. That is the entanglement, quantum entanglement. There are measures like quantum discord, entanglement. So these are the quantum measures. So how do we do the quantum mechanics here? So as I said, fluctuations. So usually these fluctuations are the amplitude of fluctuations are described by Muganov-Sasaki variable V, and this is the Lagrangian associated with this Muganov-Sasaki variable, and this alpha is basically as I said, these fluctuations interact with the background when the size of the fluctuations become comparable to the Hubble radius, right? So this alpha is the interaction, interaction of this fluctuation with the background. And this is the whole Lagrangian associated with this the amplitude of fluctuations. Okay, so this alpha basically the function of time, which is a function of explicit function of scale factor, which is how it determines the distance between the 2 points in the universe and rate of expansion of the universe and its derivatives. Okay. So the simple thing one we can start is, of course we have to do the quantum mechanics in real space, but the simple thing we can start with in study the quantum mechanics in Fourier space, right? What is simple here is that all the fluctuations, all the, I mean, if you decompose the fluctuation in terms of Fourier modes, all the amplitude associated with these fluctuations evolve independently. Okay, so we can study the quantum mechanics of each mode separately. We can associate this, quantum canonical, I mean, the commutational relations separately and study the quantum. Okay, so in Fourier space, the Lagrangian is just this. So this is a Lagrangian associated with, the production of two particles. Particle going in k direction and particle going in the minus k direction. So if you see, the one of the main problem working in Fourier space is that the V, the amplitude of the fluctuation V in Fourier space is not Hermitian. Okay, so in real space it is Hermitian, but in Fourier space it is not Hermitian. So, but in order to analyze this, quantum mechanics or the evolution of fluctuations, quantum evolution of fluctuations, we need to work with Hermitian operators, right? So one thing we can do is that just split the Muganov-Sasaki variable into real and imaginary part and work with real or imaginary part separately. That is one thing. Or we can make different real operators from the space phase variables like Muganov-Sasaki variable and from the momentum and work with those canonical variables. So if you work with real and imaginary part of the Muganov-Sasaki variable, what we get is the Hamiltonian associated with a simple harmonic oscillator for each, real or imaginary part. But this harmonic oscillator is actually a time dependent harmonic oscillator. So we know how to do quantum mechanics associated with this time dependent harmonic oscillator. Okay. So if we take some other set of variables, say some other combinations of Muganov-Sasaki variable and the associated conjugate momentum, then we can get different sets of real operators. Suppose we take this kind of, then we get this is one x k is basically amplitude of one oscillator and x minus k is amplitude of another oscillator, okay. And pi corresponding conjugate momenta. So this is actually the two oscillator. The Hamiltonian is kind of Hamiltonian of a two oscillator interacting with each other. Then the interaction strength is actually determined by the alpha. Alpha is something, the coupling between the the fluctuation and the background universe. Okay, so basically this Hamiltonian gives entanglement because of this entanglement between this k and minus k. Yeah, so we can we can do this quantum mechanics in some real inflationary models. So in slow roll inflationary models, what we know is that this if you use that real and imaginary part of Mugono-Sasaki variable, then what we get is that in phase space, in slow roll inflation in space, the dispersion towards the v square direction, the position direction will be larger than the dispersion along the momentum direction, which means that the state or the space phase is fused in one of the direction. Okay, suppose we take another example like the slow roll, and there is an ultra slow roll and slow roll regime, which is a famous model for producing black hole primordial black hole formation. So in this type of models, what is going to happen is that during the first slow roll, this phase space is fused in one direction, and when there is an USR phase where this and during that time this fusing becoming in the other direction, to the momentum direction, and then the universe evolve into the final slow roll phase. There the evolution become again towards, I mean, the fusing becoming again towards the position direction. So this the entanglement entropy also we can calculate in a similar way. Like we have to reduce, we have to trace out the one of the system and find the entanglement associated with the one of the system and calculate entanglement entropy. And what we see is that it is proportional to the squeezing parameter R, which is, as I said, it has a devolution something like this. First increases, decreases, and increases again. So the entanglement is also increases, decreases, and again increases. So yeah, that's it. So I mean, this is the basics of quantum mechanics in a simple setup, but there are more things one can do. So we have explored different aspects of quantum mechanics in different models, like in multi-field models and when there is a magnetogenesis during inflation, and for if we use the coherent state as initial state, we can do the similar quantum mechanics. And but in in reality, we have to do quantum mechanics in the real space and find out how much quantumness is buried in the correlation functions in real space, right? So there are papers calculating this entanglement in real space, quantum entanglement in real space between the two patches in the patches in the universe. And if the distance between these two patches are larger than the Hubble radius, then the entanglement is almost zero. So that's what the result. But that is for the de Sitter. So there are more things to do if you assume the slow roll, as Sriram said, that the de Sitter is just an approximation. So if you do more realistic inflationary models like slow roll inflation or multi-fleet inflation, bouncing model, what are these correlation, I mean the quantum entanglement in the in the real space is still a open question. Thank you.
Question?
Sorry, I didn't fully understand. So your initial question was whether the origin of fluctuations are classical or quantum.
No, it is quantum that we know. The question is how much quantumness is inside these correlation functions. So whatever we measure from CMB or in the large scale structure. So that is the.
You are asking how much quantum it is.
Yes.
I see.
How to measure? How to quantify? Yes.
And this you are trying to quantify by some quantum entanglement. But what exactly the observable is? Can you just?
Okay, there is entanglement. These are derived from the correlation function. So that we can construct one quantity called logarithmic negativity,
Mm-hmm.
which is actually we can construct from the covariance matrix.
From?
Covariance matrix, like from the
Mm-hmm,
correlation
mm-hmm.
functions, and also there is called quantum discord. That is also one can construct from the correlation functions.
And they tell you about, so you don't have a like Bell inequality kind of a
Yeah, that
measure.
also one can do. So I forgot to mention in the slide. So that also we can do, but in continuous space, we have to. This is a continuous variable, right? So
Mm-hmm.
we have to construct a pseudo spin operators associated with because these are not spins, right? We have to construct pseudo spin
So
operators.
these are entanglement. What kind of entanglement? What space you are computing this entanglement
Okay,
in?
these are entanglement between the two structures in the universe. Okay, so how these two structures in the universe are connected quantum mechanically?
No, I'm saying that is, as you said, this is not spin space entanglement. So
Mm.
this is some momentum space in entanglement. Is a
Yeah, so whatever I have discussed is in momentum. So here, whatever I have discussed here,
even in classical physics, there is the same.
so this entanglement generation is due to the expansion of the universe. This alpha, that's it.
So you have a alpha term which is a coupling between Vk and Vk prime, or in other words V and momenta, right? So you can always do a canonical transform and then make it diagonal, right? And so then so classically they are all equivalent, whether
Hmm.
because canonical transform doesn't change the system, it's just different variables. But quantum mechanically you are saying that they will be very different.
No, no, quantum mechanically, I'm not saying they are different. The measures will be different. So actually, if you use this real and imaginary part of Mugano-Sasaki variable to study the quantumness, what we get is the phase space is skews. Okay, so this squeezing is manifested in the other set of variables as quantum entanglement. Both are quantum mechanical quantities, measures, but it is manifested in different avatars. That's it.
Another question is, you studied the ultraslow role. So when you have coupling between Vk and Vk prime, so one is a growing mode, which is actually a constant mode, and a decaying mode. This will introduce entanglement between the constant mode and the decaying mode.
No, no, no. Actually, here I am talking about the entanglement between k and minus k.
Yeah, that is fine.
Right?
But in USR maybe you will have such a thing.
No, no. There is no coupling between decaying and.
No. When you compute Vk prime, the decaying mode will be the dominant one.
Mm.
So will there be coupling between them? There will be, right?
No, one thing is that we have to associate this canonical commutation relation between two systems, right? So there is no such association, this canonical commutation relation between these two modes, right? Those are not independent. I mean, those are the same.
Thank you.
I have a very naive question. So, of course, during inflation, this perturbations are being generated quantum mechanically. But at some point of time, it has to become classical, right? The general notion is that when it becomes super horizon, so the squeezing parameter will be very large, and it will become classical. So, whatever Jerome Martin and Vincent has seen here, that there is no entanglement, it is a signature that this perturbations have become classical upon super horizon modes, right?
Correct.
So, how do you measure the quantumness of of the modes which have been generated in the sub-horizon mode? Because once they cross the horizon, they has to become classical, right?
Okay, so there has to become classical. That is approximated statement, no? Like.
But if it is not becoming classical, then how it can seed classical structures?
That is true, but I mean the dominant contribution is classical, coming from the classical correlation function, but there can be quantum correlation functions. But as you said, from these papers, what they are analyzed is that how much quantum entanglement is there in real space correlation between these two patches or two different points in the CMB. So they are saying that in de Sitter limit, so there is no entanglement if the point is, if the distance between the 2 points is larger than the Hubble radius. Yeah, that is true. So in principle, we cannot measure.
Yeah. Okay.
Okay.
But if you do for slow roll or some other models, I don't know, there may be some signatures.
Why?